Now we're going to talk about group theory problem 1 from the January 2017 qual. And this problem says, let G be a group of order 8 times P for P an odd prime. We want to prove or give a counterexample to the statement that G has a proper non-trivial normal subgroup. And we're going to prove this statement. So notice that the size of G is equal to 2 cubed times P. And so then by Celo's third theorem, the number of Celo 2 subgroups is equivalent to 1 mod 2, and it divides P. And so since P is prime, its only divisors are 1 or P. So then in 2, the number of Celo 2 subgroups is 1 or P. So if the number of Celo 2 subgroups is 1, then we're done, because then we would have a unique Celo 2 subgroup, which is proper and non-trivial and contained in G. So then we're going to assume that the number of Celo 2 subgroups is equal to P. And so now, by Celo's third theorem, we want to consider the possibilities for the number of Celo P subgroups. And it's, for the same reason, equivalent to 1 mod P, and it divides 8. So notice that the only divisors of 8 are 1, 2, 4, and 8. And we're going to continue by cases. So case 1 is when P is greater than 7. So the very first prime after 7 is 11. So then we want to keep that in mind for any primes larger than or equal to 11. So suppose that P is greater than 7, then every divisor except for 1 is inequivalent to 1 mod P. This is because, well, 1 is equivalent to 1 mod P in this case, the smallest case being 11. 2 is equivalent to 2, and 4 is equivalent to 4, and 8 is equivalent to 8. So the only value that the number of Celo P subgroups could take is 1 for any primes larger than 7. And so then we have a unique Celo P subgroup, which is proper, non-trivial, and contained in G. So then in this case, we're done. Every prime larger than 7 for groups of the order 8 times P have a unique Celo P subgroup. So now we're going to consider case 2. And case 2 is when P is equal to 5. So in this case, it's virtually the same as in case 1. Every divisor of 8 besides 1 is equivalent to 1 mod 5. This is easy to see because 1 is equivalent to 1 mod 5. 2 and 4 are equivalent to 2 and 4 mod 5. So the only one that might have an interesting situation is 8, and 8 is equivalent to 3 mod 5. So that means this forces the number of Celo 5 subgroups to be 1, and so we're done. Now, case 3 is when P is equal to 7. So if P is equal to 7, note that the possible values for the number of Celo 7 subgroups are 1 and 8, because 1 is equivalent to 1 mod 7, and 8 is equivalent to 1 mod 7. So then if the number of Celo 7 subgroups is 1, we're done, because then we would have a proper non-trivial normal subgroup. So let's assume that it's 8. So now, if we do so, we've accounted for 56 minus 48 elements, which leaves only 8 elements left. So that would force the number of Celo 2 subgroups to be equal to 1. So you can either think of this as a contradiction to the fact that the number of Celo 2 subgroups is not 1, or you could see that in either case, either the number of Celo 2 subgroups is 1 or the number of Celo 7 subgroups is 1. But either way, we know that there is a normal Celo subgroup contained in G when P is equal to 7. So now we're going to consider case 4, and this is when P is equal to 3. So note that the size of the group is 24, and the only divisors of 8 equivalent to 1 mod 3 are 1 and 4. So 1 is equivalent to 1, 2 is equivalent to 2, 4 is equivalent to 1, and 8 is equivalent to 2. So now if the number of Celo 3 subgroups is 1, we're done. So let's suppose it's 4. And so we're going to note this number of the Celo 2 subgroups of G to be Q1, Q2, and Q3. So now we're going to let G act on the Celo 2 subgroups by conjugation, and let this have permutation representation phi from G into S3, because we have 3 Celo 2 subgroups. So now the size of S3 is 6, so phi is an onto map onto S3. And so by the first isomorphism theorem, we know that G mod the kernel is isomorphic to the image of phi, which is a subgroup of S3. So then we know that the size of G mod the kernel has to be less than or equal to 6. And so that forces the kernel to be greater than or equal to 4. But we wouldn't be done because we also need to make sure that the kernel is not all of G. So by Silo's second theorem, all of the Silo 2 subgroups are conjugates to one another. So we know that the size of the image has to be greater than or equal to 3. And hence, this forces the size of the kernel to be between 4 and 12, with 4 included. So then we have that the kernel is normal in G, and so we have a proper non-trivial normal subgroup because the kernel had to be less than 12, which means that it's proper and contained in G. And so then we're done. Great.